The next concept we're going to deal with is the notion of curvature. Curvature is usually associated with the extent to which a curve bends. Intuitively, if you think about it, a straight line has no curvature. So the curvature would be zero in whatever definition of curvature you have. This circle at any point, or at least on the circumference of the circle, the bending tends to be the same. So the curvature of a circle for a given circle would be constant. In general, if you're moving along a path that is windy, as like for example when you're driving, you notice that you will be adjusting your steering wheel to a different extent of the bend. So along such a path, the curvature would be dependent on where you are on that path. So it is time dependent, or it is dependent on your deep independent variable. So whatever concept of curvature we come up with, it needs to take in these built-in concepts. Also, for example, if you take a very small circle, it tends to be, the curvature is constant, but it tends to be different from the curvature of a very large circle. So a larger circle has a curvature that is small because it's moving more and more towards a straight line. A very small circle bends a lot, so the curvature is constant, but it is large. Okay, so these are some of the ideas or intuitions that need to be built into the notion of curvature or the formula for the curvature that we come up with eventually. So quickly, just to recall from the last time, so let's recall the notion of unit tangent vectors, etc. We said that if vector r was your position vector, positioned i.e. at the origin, and its final terminal position is on your parameterized curve, then your tangent is given by r dot, and the vector u is a unit tangent vector. So the vector u, recall, would be the tangent vector, which is the vector r dot, divided by the magnitude of vector r dot. So this would be a unit tangent vector. And we said that we defined the arc length variable as s. S would be the integral of the mod of r dot. So that's your indefinite integral. So that the unit tangent vector could be written as r dot over ds dt. So that if we write r dot as dr dt divided by ds dt, we have that the unit tangent vector can also be written in terms of s as the derivative of the vector r with respect to the arc length variable s. So this is how we sometimes denote the unit tangent vector. So we can say i.e. vector u is then, can be written in that fashion. Of course, in the complex case, we don't have the notion of a vector, but the unit tangent would be given in terms of your function z of t, where z is your complex number tracing out the curve on a complex plane. So in the complex case, the unit tangent, it's not a vector now, just given by in a very similar way, z dot divided by the mod of z dot. Recall this mod would be your complex mod. And if we write the z dot as, or rather the equivalent of the arc length, so if we define here the arc length to be the integral of the mod of z dot dt, then we could write this as the unit tangent as z dot divided by ds dt. So that here u would be equivalent to the above, as your z dot could be dz dt divided by ds dt would be dz ds, like so. So this is your unit tangent. even though the unit tangent vector and the unit tangent in the complex case are written in terms of the arc length variable s, the computation of these would of course revert to writing everything in terms of t, usually the time variable. Okay, so now let's do a number of examples dealing with the unit tangent vector before we go on to defining the curvature. Okay, so in the first of these examples, let's look at a number of examples. In the first example, suppose your vector r is given by hyperbolic cos t, root 3 hyperbolic sine t, and your z coordinate is simply t. So t is your parameter. Right, so for the unit tangent vector, we'll need the tangent vector itself. So here, therefore, vector r dot would be derivative of hyperbolic cos is hyperbolic sine. Notice there's no sign change as in trigonometry. The derivative of hyperbolic sine is hyperbolic cos, and the derivative of t is 1. If you divide this vector by its magnitude, we get the unit tangent vector, vector u. So from here, first of all, the magnitude of the vector r dot would be the square root of hyperbolic sine squared plus root 3 squared hyperbolic cos squared plus 1. So we've got hyperbolic sine squared 3 times plus rather. So let us erase this. So that should in fact be plus. This is hyperbolic cos squared t plus 1 being 1 squared. Right. In the hyperbolic functions, 1 plus hyperbolic sine squared is hyperbolic cos squared. So this is slightly different from trigonometry. So 1 plus hyperbolic sine squared, we're going to replace by a hyperbolic cos squared. So this is a hyperbolic cos squared t plus 3 times hyperbolic cos squared t. We add that and take square roots. We end up with 4 hyperbolic cos squared. So this is 2 hyperbolic cos, which is cosh. There we go. So that's the mode of r dot. So that therefore, the vector u would be the vector r divided by its magnitude. So the magnitude of r dot. So vector u, the unit tangent vector, therefore, is r dot divided by this. So I'm going to divide each component. Well, let's write this thing as 1 over 2 hyperbolic cos of t. This is 1 over the mod of r dot multiplied by the vector r dot. And once we have that, we can write the unit tangent vector in terms of its coordinates. So dividing each of the components of r dot by 1 over 2 cosh, we end up with, keeping in mind that hyperbolic sine over hyperbolic cos is hyperbolic tan. 1 over hyperbolic cos is defined as hyperbolic sec. So this would then be removing half outside. If you simplify that, divide r dot by hyperbolic cos, we end up with hyperbolic tan. Then we get the second component as hyperbolic cosh divided by hyperbolic cosh. That would be 1 times root 3, that's root 3. And then we get 1 over hyperbolic cos, which is hyperbolic secant, hyperbolic sec. That's your unit tangent vector in this example. In the next example, we'll deal with with an example from the complex case. So in example B, if the previous example was example A, we have the complex Z equals t e to the I t, t e to the I t. Perhaps we should make this thing look nicer. That's the end of the previous example. And this is t e to the I t. There we are. So in this case, the derivatives and the tangents and so on are not vectors. However, what we get from this is that z dot, now applying your usual product rule, would be 1 times e to the it plus t times the derivative of e to the it, which is e to the it times I. We get that. That can then be simplified as 1 plus it multiplied by e to the it, removing e to the it as a common factor. When we take the mod of this z dot, that will be the mod of 1 plus it times the mod of e to the it. So that therefore, the mod of z dot is equal to the mod of 1 plus it in the complex sense times the mod of e to the it. And you recall I said e to the I theta always has a modulus of 1. So the e to the it has mod 1. The mod of 1 plus it is very simply the square root of 1 plus t squared. Recall that the modulus of a plus ib is a squared plus b squared. So z dot then divided by the mod of z dot gives us the unit tangent. Not the unit tangent vector, because we don't have the concept of a vector in this case. So therefore then, the unit tangent u, which is z dot divided by the mod of z dot, is 1 plus it e to the it divided by the mod of z dot, which is the square root of 1 plus t squared. That's the equivalent of your unit tangent vector. In example C, we have an example that looks somewhat elaborate, but it simplifies to something quite interesting. So suppose vector r equals 2 ln of the secant. This is now the trigonometric secant t, 2t, and then the log, the ln of sine t. All right. So in this case, the r dot, that means differentiating each of those components, the r dot is the vector given as follows. The derivative of log of sec is 1 over sec multiplied by the derivative of sec. So the derivative of sec is sec tan. So what we end up with is 1 over sec times sec tan, which is then very simply tangent, trigonometric tangent. The derivative of 2t is 2, and the derivative of log of sine is 1 over sine times the derivative of sine. So it's 1 over sine times cos, that's cos over sine, so that's cotangent of t, like so. So take r dot divided by its modulus, by its magnitude. We need to determine the magnitude of r dot. So here, the magnitude of r dot would be squaring each of the components, adding them up, taking the square root. So we get the square root of 4 tan squared t plus 4, that's the 2 squared, and then the cot squared is cot squared of t. Summing that up and taking the square root should give us the mod of r dot. Okay, so what we can do here is write everything as a common factor, keeping in mind that we can write this as a perfect squared, in fact, right? So if we write this as a square root of, notice, 2 tan t right, plus the cotangent of t, right, and square all of that, like so. So if you just check this, the first term squared is 4 tan squared. The second term is cot squared. The middle term will be, you multiply the two, so you got, for the middle term, it will be 2 tan t cot t doubled, so that will give us 4 tan t cot t. Since cotangent is 1 over tan, tangent times cotangent is 1. So the middle term would be very simply 4. So that's correct. The square root of all of that, of course, then would then be knocking off the square and square root. We get 2 tan of t plus cotangent t. Just to remind you, keep in mind that in the previous step, we're using the idea that tangent is a reciprocal of cotangent. Okay, so here then, the unit tangent vector would be r dot divided by this. So this would be, incidentally, we need to be mindful here that we take the positive square root. Okay. Unit tangent vector. This will be then 2 tan t, right, 2 cotangent t. So that is your vector r dot, and you divide that by, I should say here, this step, this should have been a modulus, because we want to keep the square root positive. So this would be then the mod of 2 tan t plus cotangent t, like so. You could, if you want, write the tangent and cotangent respectively as sine over cos, and the cotangent as cos over sine, and simplify all of that. Want to very easily show that. I'm not going to do the calculation here. I'll just state the result. That you could, if you replace the tangent with sine over cos and the cotangent as cos over sine, what we end up with is that this would equal, I would say a few steps later, this can be written as 1 over 1 plus sine squared. I won't do the calculation. I'll leave you to check if you're interested. Into 2 sine squared, right? 2 sine t cos t, 2 sine t cosine t, and the third component there, left for a lack of space, is cos squared t. Close it like that. Okay, so this is obtained by converting everything to sines and coses, keeping in mind that tan is sine over cos and cot is cos over sine. Okay, so now to get to the notion of curvature proper. So like I said, when we define curvature eventually, which is what we're going to do almost immediately, we need to keep in mind some of the intuitive ideas we have of curvature. For example, like that of a circle, whose curvature is constant, like that of a straight line, whose curvature is 0, etc., etc. Okay, so we define curvature in the following way. We take since the vector u represents the unit tangent vector, we take the vector u, differentiate it with respect to the arc length, s, so that's du ds. And since the curvature is going to be a number, remember du ds will be a vector, we take the mod of du ds and define that as the curvature. So in this definition, right, we define the curvature and represent it by kappa. So the curvature kappa is defined as the mod of the derivative of your unit tangent vector with respect to the arc length variable s. Now, again, we could define an equivalent concept of curvature for the complex case. There it would just be a matter of dropping the vector notion. So the curvature in the complex case, kappa, would be the complex mod of du ds. U is not a vector in that case. But if you come across an example like that, we need to keep that in mind. Okay, so this is what we'll call one definition. We'll introduce immediately the notion of a normal vector immediately. So that's the curvature. Another definition we're going to speak about eventually is the notion of the unit normal vector. So if you call that a curvature, let's write it differently. So in this definition, I'm going to define the normal to be the vector n would be 1 over the curvature of the path multiplied by du ds, where u is again your unit tangent vector. So essentially the normal is your du ds divided by the mod of du ds, since kappa is the mod of du ds. So it's clear that the normal is a unit vector of magnitude 1. It's a vector divided by its magnitude. So this is what we call the unit normal vector. So this is the unit normal vector. So if you want a bit of a picture, if you have a curve, a path that, remember your vector r is your position vector that would have started at the origin and end up on the curve itself. The tangent vector would be tangential at the point of contact, and the unit tangent vector is the vector u. That's the one of magnitude 1, and your normal is generally the normal that is perpendicular to the tangent vector. So that would be, for example, the equivalent of your normal vector. So this is an attempt to look at this in 2D. You've got your new unit normal vector, you've got your unit tangent vector, and of course your position vector is your vector r. And your path is the curve that is traced out. Okay, let's do some examples in this regard, i.e. determining the curvature of certain curves. And of course, the first one, the obvious one that comes to mind that we'd like to deal with is the circle of radius a, say. So this is examples. So in A, let's consider the circle of radius a. And we know that the circle of radius a in parametric form is given by, in vector form, the vector r given by a cosine t or theta, whatever you want to use, right? A sine t. Let's keep the parameter t. You may use the theta if you want. Right, to determine the curvature of this, we need, of course, the unit tangent vector and then differentiate the unit tangent vector with respect to the arc length. So let's start. So you've got vector r dot, that's the derivative of the vector, which is minus a sine t, a cosine t, and then we of course need also the mod of this r dot. So therefore the mod of this vector very simply would be, it's clear, square the first component, the second component, add, take square root, we end up with a. And a is positive, of course, the radius of the circle. Therefore then, and incidentally, this would of course be ds dt also, because ds dt is the mod of dr dt. Keep that in mind. That will come up quite often. So therefore then, the unit tangent vector, which we denote by u, is 1 over the mod of r dot, which is 1 over a, like so, times r dot itself, which is minus a sine t, a cos t. That's your unit normal, unit tangent vector rather. And if you simplify all of that, we end up with very simply minus sine t cosine t. Right. If you differentiate this vector with respect to the arc length variable s, we end up with, and of course then take the modulus of that, etc., we'll end up with the curvature. Okay, so just to recall then, the du ds, therefore, is determined by, well, we have to convert everything to t's, so this is then du dt divided by ds dt, chain rule, okay? Du dt is differentiating your vector u, your unit tangent vector, with respect to t. So if you differentiate that, we get minus cosine t, differentiating u with respect to t. Derivative of cos is, of course, minus sine, right? And we're going to divide that by ds dt, and ds dt is the mod of r dot, so that was a. So this is then 1 over a, or if you want to take the minus sign out, minus 1 over a into cos t sine t. So therefore, kappa, the curvature, is the mod of du ds, okay, which is 1 over a, or 1 over the mod of a, which is positive anyway, multiplied by the mod of minus cosine minus sine. So this will be the mod of the vector minus cosine minus sine. Okay, and it's clear that the mod of minus sine minus cosine is 1. So this is 1 over a. So the circle of radius a has a constant curvature 1 over a. The bigger the circle, the smaller the curvature, as expected. Right, in the second example, we'll consider an example we considered earlier on. Let's go back to the example vector r given by hyperbolic cos root 3 hyperbolic sine. We have it further above, and the z coordinate is t, for which we want to determine the curvature, whatever the curve looks like. We had shown earlier that the vector, just recalling that the vector u, the unit tangent vector, is in terms of hyperbolic functions 1 over 2 into hyperbolic tan. This is what we showed earlier, of course. Root 3 and hyperbolic secant. We also recall that the mod of r dot, which is ds dt, so ds dt, which is essentially the mod of dr dt we showed earlier, this was equal to 2 times the hyperbolic cos of t. So this is all from previous. So to find the curvature, we need the derivative of u with respect to s, and for the derivative of u with respect to s, we need the derivative of u with respect to t, etc. So let's just recall what we need. And now, du ds, right, would be given by du dt, chain rule again, divided by ds dt. ds dt we have already, it's 2 hyperbolic cos. All we need is du dt. For that we differentiate the function u, or the vector function u. Du dt, right, is given by, well, that's equal to a half into the derivative of hyperbolic tan is hyperbolic secant squared, sec squared. Derivative of root 3 is 0, and the derivative of hyperbolic sec. Now, unlike in trigonometry, derivative of sec is sec tan. In hyperbolic functions, the derivative of hyperbolic sec is minus hyperbolic sec tan. So yes, this is minus hyperbolic sec, hyperbolic tan. Right? So what we could do is remove a hyperbolic sec to get half of hyperbolic sec into hyperbolic sec 0 minus hyperbolic tan, like so. Take this and divide it by ds dt, we have du ds. So let's do that. So that now, therefore, du ds will be equal to du dt. Let's rewrite du dt. This is a half hyperbolic sec into hyperbolic sec 0 minus hyperbolic tan, right? And if this is du dt. Divide that by ds dt, and ds dt we showed above is 2 hyperbolic cos. Okay, we can simplify this keeping in mind that 1 over hyperbolic cos is hyperbolic sec, or 1 over hyperbolic sec is hyperbolic cos. Right, so this simplifies as 1 over 4. Take the hyperbolic cos at the bottom to the top as hyperbolic sec. We end up with hyperbolic sec squared into hyperbolic sec 0 minus hyperbolic tan t, like so. That is du ds. The mod of this gives us the curvature. So therefore, the curvature kappa, which is the mod of du ds, is equal to, well, the quarter hyperbolic sec squared is positive. That goes out as a factor. Hyperbolic sec squared t. And then the modulus of the vector hyperbolic sec 0 minus hyperbolic tan is going to be, well, in simplified form, hyperbolic sec squared plus 0 squared minus hyperbolic tan squared gives us plus hyperbolic tan squared t. Like so. Let's squeeze in the t there. In trigonometry, secant squared minus tan squared is 1. In hyperbolic functions, hyperbolic secant squared plus hyperbolic tan squared is 1. So this then simplifies as 1/4 hyperbolic sec squared t, being the curvature of the curve we had earlier on, namely vector r. It is interesting that if you look at the vector du ds, right, it can be written as, well, let's just notice this. That's quite interesting. Let's just look at du ds. Notice, like I'll say it, notice. In fact, let's use a different color. Notice that du ds at this point, just looking at it from previously, that's looking at it from there, right? If you look at du ds, that factor 1/4 hyperbolic secant squared is in fact kappa multiplied by hyperbolic sec t 0 minus hyperbolic tan t. The unit normal that we defined earlier on has the form exactly this. So we know that the du ds, if you just look closely, is in fact equal to the curvature times the unit normal. If you look at the definition of the unit normal, this is exactly what we have. So we conclude write here, therefore, that the unit normal will be equal to the vector multiplied to the curvature, which is hyperbolic secant t 0 minus hyperbolic tan t. Voila. One could, of course, perform similar calculations with equivalently for a path given in complex coordinates. I'll just mention one or two steps without doing the complete example. Right? In the third example, if you looked at the old z equal to t e to the I t, we showed that the unit tangent, not the unit tangent vector, just the unit tangent, is 1 over 1 plus t squared square root, like so, 1 plus it e to the it, and we also showed that ds dt, which is the mod of z dot, ds dt, which is the mod of dz dt by definition, z replaces the r dots, is square root of, we showed 1 plus t squared. That's what we had before. So if you wanted the equivalent curvature, you'd have to compute du ds, etc. So du ds would be, by the chain rule, first of all, du dt, ds dt. Okay? Du dt, well, take your function u and differentiate it with respect to t in whatever form you're going to do. So there's u, differentiate that with respect to t, differentiated of course, ds dt divided by 1 plus t squared, like so. And then take the modulus of that. And of course, your curvature would be the mod of du ds. Keeping in mind, of course, that in this case, this mod is the complex mod, as always, in the complex case. I think we'll stop there as far as curvature is concerned. We are all going in curves and circles and who knows what.